About our team. I'm an SRE, I'm in the platform area. I'd like to share with you this story. Is about a POC that we did with AWS 6 months ago, roughly, between November and December 2019. And it was specifically targeted on using AWS EKS with the spot instances and autoscaling to reduce at the minimum the costs on running Kubernetes into AWS. So I will share my screen. Probably I can do this. Is it visible?
Yes.
Thanks.
Yes, it is.
Okay, so autoscaling Kubernetes on AWS for fun and profit, a story. As I said, I'm part of an SRE team, and lastminute.com is a travel company. So we sell flights, hotels, and we have a lot of activities that require a broad infrastructure. Lastminute.com has been pioneering Kubernetes adoption since 2014 with version 1.3, I guess. I was not in the company at that time, but I joined the company 3 years ago. Mostly because I wanted to get into Kubernetes and I knew they were using Kubernetes for their core infrastructure. So historically, Lastminute has been running in a data center. And last year, between October and December, we were asked by the management if we could evaluate migrating to AWS. So port our applications in the cloud, in the public cloud, to leverage mainly the scalability features of public cloud. So being able to scale down the infrastructure when not necessary, and instead being able to grow the infrastructure when we need it. So this is a story of how we did it and the overall experience we had with AWS, with some tools that we adopted and some techniques that might help you as well operating in such scenario. So, but before we get into it, a little bit of agenda. So the first thing would be our motivations to go to the cloud, our goals that we set for the project, and our challenges that we knew we had to face. The technologies involved, so basically our tool set. Some practices that are well defined in our company, like infrastructure as code and security by design. How we actually did it, so how we actually implemented autoscaling infrastructure inside Kubernetes with EKS. And a note on cloud readiness, which means basically that infrastructure is not enough. The application needs to be bundled with infrastructure to be cloud ready and to leverage cloud native deployments. And in the end, the results and some further improvements that we are left off when we will go effectively into production. So motivations, I hope you find funny about this meme, but it's basically the truth. So we as an SRE team, were very happy to start working with AWS because, as I said, Lastminute has been historically running in a data center. Mostly of our infrastructure is on premises as of today. We did have some implementations, some QA environments in AWS. We also have GCP, we also have Azure. So, but we've never put the cloud at the core of our infrastructure. And for that, we have an SRE team that feels the burden of having to manage a lot of the, let's say, peculiarities of a data center, like remote hands, hardware to be replaced, alerting about disks failures, networking problems, etc., etc. So when we look at AWS, we are just like the guy there. Lots of automation, lots of API to drive infrastructure manipulation, and also destroying and creating infrastructure just with an HTTP call. This is very powerful. And in fact, what our motivations to go to the cloud are reducing our total cost of ownership of our infrastructure by leveraging the pay-as-you-go model in the cloud, improve our scalability so that we can get rid of resources when we don't need them, and we can instead allocate more resources only when we need them and improve our latency response time when we have traffic peaks. We need to decrease the SRE and DBA's toil caused by activities like patching and Kubernetes upgrades that we always do. And also we wanted to have development teams, product teams empowered to manage the microservices 100% autonomously. So yet we all have a lot of automation to let them bake artifacts and deploy autonomously, so they are independent. But what they don't have right now with the data center is operational capabilities that can be implemented by themselves. So we wanted to achieve also this goal. And in fact, goals everywhere. What were our goals that we set for adopting cloud technologies and for putting in place this POC? We wanted a fully automated infrastructure as code pipeline that could create, destroy, and also modify the environment as we needed, and also as the product team, so the development team needed. These, of course, should implement security by design, an effective networking model that enables communication that can be enabled by parties like private and public subnet and security groups. That is not too complicated, not too complex, but can serve our need for security and network segmentation. We wanted to have full identity and access management fully automated. And of course, we need to manage multiple Kubernetes clusters at the same time. The second goal was increase our availability over resource consumption ratio, which basically means given that you have, I don't know, 2 terabytes of RAM and 200 cores, you can serve 10 million requests per day at a 99.9% availability. Basically, you wanted to increase this availability, port it to 99.99, so I had 19, but reducing the amount of resources that we consume, so with less CPU, with less memory. And third, but not last but not least, we also want to be able to only pay what we need. So not only being able to increase the ratio of availability over resource consumption, but also being able to scale up and down, scale in and out with resources as we go. So follow the traffic pattern, workloads that can be tiered depending on their priority, and also have it safe for our customers in the sense that we don't want them to be experiencing issues while autoscaling is happening. And all of this, of course, with the big challenge of migrating container to the cloud. There are a lot of challenges that we knew we had to face just before start implementing the thing. For example, autoscaling means adding and removing resources. As long as Kubernetes already have horizontal pod autoscaling and features that ease the autoscaling, adding and removing nodes might not be as easy as it seems. So, of course, our challenge, very first challenge is do not lose any single request when scaling in and out with nodes, which means do not let our customers have a disservice for their requests. We knew that a big challenge is having resiliency while keeping the lowest spending as small as possible. No? So if you want high availability, you can have 4 different availability zones, but there is a trade-off because the more availability zones, the more you will incur into cost for network between the zones or allocating resources. Another challenge is, of course, adapting the system capacity as fast as possible, which means that we cannot have 5-10 minutes long time between one node is added or removed to the pool, because by the time this time frame is passed, we already incur into losing requests. If we have a huge peak of traffic, I mean, it's a scenario that we sometimes have due to promotional campaign or big events or marketing ads, etc., etc. The last challenge, of course, which is not related to what we control the most, which is infrastructure, but is related to the code, so the applications, is having the applications be cloud ready. And so having a checklist that will enable us to declare that the application is ready for the cloud, which means that that startup and stop time of the application influences a lot scaling, and we will talk about that later. We are mainly a Java shop, and we adopted Spring with an internal framework. And the Java dependency runtime injection can be very slow for a startup. Also, we need healthiness, self-healing, and lifecycle hooks, which means the application itself must be ready to declare its healthiness, self-heal itself, and have lifecycle hooks that permits the application to be scaled up and down in a number of replicas. And last but not least, again, the application has to expose information about the resources it consumes, like caches, databases. You cannot go to cloud without knowing in very details before the billing comes how much you are consuming, because when the billing comes, it's too late for reducing it. So given these challenges, we adopted some technologies, and of course, AWS EKS, Kubernetes, which we know very well. We have a lot of engineers with long experience operating Kubernetes. We use Terraform. I'll explain why in a second. We use GitLab CI for pipeline execution. We use Helm for the product development team packaging the applications. We will use Prometheus as a monitoring system. We will have Nginx ingress controller and HA proxy ingress controller that will substitute Nginx in the V2. And then a lot of other useful tools that we found in our way, which are the cluster autoscaler, which is also part of the official Kubernetes distribution. KubeSpot termination notice handler, which I guess is now deprecated in favor of the official AWS node terminator, but we used it. Kubestate metrics is a component that we used in our first iteration. We will see that in a second. And the Zalando Incubator kube metrics adapter, which was very handy in our scaling by business metrics. The folks at Zalando have a huge and incredible team of people working in Kubernetes and giving back to the community a lot. So thank you, Zalando, and thanks Zalando SRE team. So a note about the practices that we wanted to implement from day one. Infrastructure as code. We said we are going to use Terraform, and Terraform has very good pros, but also some cons. To make the best out of it, we decided first to not have a unique project that manages everything, but divide into workspaces, each one with a limited scope. For example, we have a global project where we maintained the IAM federation, the transit gateway, main networking in terms of transit gateway associations, NAT gateways for IPs. So all the common things stays in one project. Then we have one or multiple infrastructure projects that will drive the creation of the cluster, the networking rules around this cluster, and also, accessory resources like RDS, Memcache, Elasticache, whatever. And then we might have also application projects in which we control, for example, installation of Helm packages, namespaces, secrets, etc., etc., etc. So by leveraging this distinction, you have smaller projects with a reduced scope, and usually Terraform works better this way. Obviously, you have common parts of your infrastructure that needs to be shared. And one weird trick that we have always been seen working very good with Terraform is symlinking a .tf vars around the workspace directories. And also using locals a lot help us identify same defaults, but that can be overridden in the scope of a project. So obviously, as infrastructure as code dictates, we don't want any write operations to be executed concurrently by two different team members, as long as they are on different projects. So the write operations can only be executed by a service account inside a pipeline. And we used GitLab CI pipelines for that, because we also use it for building our software. We're also great fans of GitLab. And so we don't have any risk of making concurrent conflicting changes. And we also get all the GitOps benefit, like being able to do auditing and tracking of our requests, and also point-in-time recovery. So we can just roll back to any previous commit and just reapply that commit, and Terraform should, 99% of the time it works properly, replace your infrastructure with what you have in that commit. And also, of course, isolated execution. So we want to be able to carry on projects in different workspaces in parallel. So we used data and the outputs to make the most out of it, to interpolate objects. So for example, we have the data of a transit gateway that gets filtered inside the other project that needs to access the transit gateway data. And here an example of our global infra. So this is the global project, in which, for example, we define a VPC that is going to be shared via the transit gateway with all the other VPCs. And you can see the very good part of Terraform is, being able to define variables, being able to define static content where you need it, or just refer to data, like, for example, the NAT gateway elastic IPs, where you will need them. Also, again, the reason to have Terraform for us is that for AWS is very well supported. I guess AWS is one of the most covered provider in Terraform. You often find inside the Terraform resources, the same day a new release a new product is released on AWS, you find it in a Terraform resources, because the two companies often work together. Also in the team, Terraform is very well known. We adopt it quite a lot. And it's kind of easy to iterate locally inside your local project before sending the change to the pipeline for being executed. Of course, there are downsides of Terraform. Well, obviously, it's not real code, but it's text. So the infrastructure as code purists will not accept it, because like there are projects like Pulumi or Metaparticle that are indeed software that you can run to spin up and manage infrastructure, which is more testable and probably not as stable as Terraform is. And of course, you don't have built-in rollbacks, and the whole thing is declarative. So this is another downside. Every time you make an error, because you will make errors, it's a roll forward that will have to fix your error. You cannot have a built-in rollback inside the Terraform execution. And here, just an example of the same project, Global Infra, in which we run the pipelines. So we have several stages. Each one of those will create a plan and verify that it's syntactically valid. Then we'll apply to the QA environment and maybe run some tests. Then we'll move on into validating the production configurations and applying and testing, etc., etc. So as you can see, we are able to iterate quite a lot. We did 63 iteration of the global project in 2 months. The other two were fairly higher numbers, probably in the range of 200 iterations. And this is, very powerful, in my opinion. We use it as a measure of coordinating ourselves with Git, which is effectively good for a team that is 15 to 16 people. Although only 8 people worked on this. Also, another practice that we wanted to adopt as starting from day one is security by design. What this means is we don't want, for example, credentials to be spread around people, or having secrets inside the applications. Rotating credentials is by far the most security impacting activity that you can have in a company. So this is an example. This is a graph of how we did it. So avoiding to have secrets that needs to be managed in your infrastructure. We did it this way. So I will take the pointer. So here is our team, either SRE or developer. We have an Active Directory in a company. So we use the Active Directory file system to federate our authentication with an IAM role. What this will do is basically we'll send an SAML token back to the user. And again, with that, you will be able to have an STS token, so a temporary session token. That token is made of credentials that you can use to then authenticate to EKS or other services. As long as you are in a proper IAM role, you will be given credentials that will allow you to access to these services. And this is already a huge win over our previous implementation of cloud infrastructure, because at this point, all we need to do is having our company credentials and setting up the appropriate roles inside IAM. So there is a regex that will match the role with your group. And starting from that, we can get these tokens and do not worry about authentication or authorization anymore. But this is not the most important part. The most important part is how applications will leverage this mechanism to access other resources in the cloud. Very often, sticking credentials, even with secrets inside your application, can lead to security issues. And this because, if they are long-lived secrets, and the application is compromised, these secrets could be leaked. And if one secret is leaked, basically those are API services. You can call them. So to avoid this, what we have is that we used a feature that was just released, like in September 2019, and that's IAM roles for service account, so IRSA. With this new feature, basically IAM acts as a provider of credentials, even for Kubernetes cluster. Kubernetes cluster will have an IODC implementation that will act as a federation for IAM. So the pods that will be spawned, that will be run in the Kubernetes cluster, if you annotate the deployment of these pods with a special annotation that contains the IAM role, the deployment request will be intercepted by a mutable admission plugin in EKS that will inject into the environment the STS token credentials that the pod then can consume to authenticate to other services. And this has been exposed also in the various languages SDKs like Java, Go, PHP. So inside your application, there is a method that you can call to authenticate with these credentials against the services. And also this is very powerful because it allows every developer to just basically forget about authenticating or authorization to a service. Hello? I heard someone wants to do a question, maybe?
I have gathered the questions and will ask you at the end. Okay.
Okay. Awesome. Thanks. Thanks, Arash. Okay. With that, yeah, this is also an image of our security first approach. So managing security groups is a very powerful way of giving visibility of a network configuration. So as well as managing credentials can be completely transparent, managing network isolation and network segmentation can be completely transparent for the user and can be represented as text. So it can be parsed, it can be read, it can be discussed in code reviews. Here, just an example of how, for example, we created an ingress rule for our cluster HTTPS endpoint for the API. You can see that it's very easy to see the port, the protocol. So a security team that might not have any experience with AWS could just be, or Terraform, could just be taught about the syntax, and they could be able to have a grasp immediately on the potential problems that could arise in a network configuration. And also this was a good approach because enabled us to work with security in a much faster way than it would be, for example, to produce network graphs from an appliance or using some other techniques like we other do in the data center. Okay, so we now go into the real implementation of our autoscaling with EKS. And there are going to be several iterations. So the first thing that I'd like to discuss is a pretty big difference between autoscaling and having spot instances. You don't need spot instances. You can actually achieve pretty decent results just with autoscaling. And this because you will still have to pay the full on-demand instance, but as long as you are able to scale in and out with your capacity, you are going to save already a lot compared to a data center where you buy hardware and you rack it and it's there. So you have already paid for it. So this was our first iteration. I will make it a little bit easier on the components. So what we have here, of course, is our EKS service managed by the EKS Terraform module, which was very handy for us, was very complete and powerful. We decided immediately for the tiered workloads that we wanted to have a core worker group that has autoscaling, but is based on on-demand instances and is hosting the core components that make other infrastructure autoscale. So for example, in the core worker group, which is say pretty stable, does not require a lot of scalability, we are going to run the metrics server, which is a Kubernetes component that is able to pull metrics from the kubelet. We will run the cluster autoscaler, which is also another Kubernetes component that will read data from the metrics server and will scale the other worker groups. And we will run kube state metrics. So initially we adopted kube state metrics, which is an exporter towards Prometheus of the metrics generated by metrics server. So as I said, the core worker groups, of course, are Kubernetes nodes. They will run mainly kubesystem or other namespace dedicated to making the other part of infrastructure scale. And so with the EKS module, we created an on-demand worker group made of on-demand instances of just one type. And the Kubernetes node inside here are continuously sending data, exposing data about the say the number of pods that they want to have, that they are running, and if they have available capacity. So using horizontal pod autoscaling V1, based on the CPU and memory metrics for a specific deployment, we were able to initiate some scale actions, either up and down, when the CPU, the average CPU of pods for a certain workload were going too high or too low. This is the Nginx ingress I was mentioning earlier. So in a customer, let's say, point of view, the customer will reach the load balancer made by Nginx ingress controller. The Nginx ingress controller will dispatch requests to the workloads that have the HPA v1 enabled in a cluster. The workloads will be exposing their CPU via the kubelet to metrics server, and the cluster autoscaler will say, oh, look, I am configured to have no more than 50% CPU as an average for the pod in 5 minutes. So since the CPU is now at 75%, I will initiate a scaling action to increase the capacity of this worker group. And although this actually works, we were not really happy with it because scaling on CPU is not very effective and is also not very fast. You might end up, very, very soon into performance degradation of your applications because the CPU is registered, let's say, in a sampled way. So the time that it takes to grow the sample, the average, is time that you lose into being able to scale. So the time that it requires effectively to have a scaling action done is so long that your CPU is already degraded and you're already increasing latency and losing request or capacity. So in the first iteration was pretty good, but was not good enough. And we wanted to enforce before the autoscaling. So we wanted to master autoscaling first for then moving into using spot instances, because when we are able to scale in a way that is fast and is also reactive, more reactive, we can then move into reducing the cost. So we gave our challenge into controlling autoscaling first. Our goal was controlling autoscaling first and then moving into reducing the cost. So in the next iteration, in V2, we replaced some components. So, well, the core part is somewhat the same. We already have cluster autoscaled, but we already have metric server, which I was not able to draw here, but in the core group, we introduced a new component, the Zalando team developed component, Kubernetes adapter. And what this component is doing is fetching data from the deployments and from the pods out of Kubernetes, and then pulling them into Prometheus, so exposing an interface that Prometheus can call. And what this enabled, since we also changed from Nginx ingress to HA proxy ingress, right now it means that we are able to scale on much more fine-grained metrics. So in fact, we are using now V2 Beta 1 HPA API. So the horizontal pod autoscaler API we upgraded to V2 Beta 1, where we have custom metrics. And custom metrics needs an external metric server that can serve the API for these custom metrics. And this kubestate metrics adapter was exactly that. So what happens in this scenario is that we still have our on-demand worker group, but the scale actions are going to be driven by our development team and not by the CPU, which means that the ability to control when we scale is much more granular, because we do not have to rely on CPU measurement. We rely on measurement that comes directly from the application, in this case, the HA proxy ingress controller number of connections per backend, and the application's garbage collections time. Because we use Java mainly, our garbage collection is what drives the need to scale in and out. So with this iteration, and also with making the application respond faster to scaling action by reducing the startup time, we were able to scale much faster than V1. And we would have been happier if we could also have been able to tune the parameter of how the HPA controller inside EKS manages thresholds for scaling. But since EKS is a managed service, you don't have really control on the configurations of it. So we worked with AWS to see if there was a way. Actually, turned out that there wasn't, and probably will never be. Basically, you will never be able to configure the controller inside Kubernetes in EKS as of now. But we were able to introduce custom metrics that was way much more granular, and that enabled ourselves to see these scale actions happen much faster. So since that we now mastered autoscaling, I also have an example here of the Helm was configured, because this is relevant. So we use Helm for packaging application, and we moved our autoscaling driven with an option from autoscaling v1 to autoscaling v2 beta 1, adding the annotations that are then used by metrics server, metrics adapter. So these annotations that represent the queries that you can do to Prometheus to decide the scaling actions will then influence the value of the target average value that you want to achieve. So the way this works basically is Kubernetes Adapter will pull the data out of Prometheus and will evaluate if there is a scaling action that needs to take place based on the metrics you configure. So with this, the team was completely autonomous in deciding when the scale actions should happen, and this was a huge win for us. But then we were not happy yet because still costs were pretty high, and so we moved into evaluating how we could save money using spot instances. And it turned out that we could replace the on-demand worker group completely with a spot worker group. Although, since the spot instances are not guaranteed to be up and running, they can be terminated at any time. In a 3.1 iteration, we reintroduced the on-demand worker group to have, let's say, a sort of minimum of workload available all the times. But most of our workloads was moved into the worker group made of spot instances using the EKS module launch template. And now these deployments are still routed via the HA proxy ingress, but now these deployments are spread into multiple worker groups, and these worker groups can scale independently. And also using taints and tolerations, we can decide if a workload can opt into running in spot worker group. And of course, we need to understand if a node of the spot instance is going to be terminated. So we added a core component called a spot termination handler that will intercept a node termination signal by the AWS API and will instantly drain with a kubectl, with an API, Kubernetes API call, the affected node. So combine it with the application ability to wait for completion, to finish its processes, to drain its requests, and the lifecycle hooks that Kubernetes embeds into the deployment, like liveness and readiness checks. These scaling actions were able to not lose requests when we were serving workload in production with this infrastructure. So the tainting here is one of the core parts, in my opinion, because if you have workloads like stateful sets that they cannot really be playing well with scaling, with auto-scaling, you don't have to tolerate those workloads. While instead, if you are running microservices with stateless applications, this spot worker group can save a lot of money, like 70%, 60-70% of the price less compared to on-demand instances. And the way we did it via the EKS module is this one. So in the EKS module in Terraform, you have worker groups and worker groups launch templates that are both lists of maps. Here I collapsed the core worker group, which does autoscale, but it's probably never impacted by autoscaling because the CPU is so low there. We have our on-demand instances of one type, which we have a size. And in here, we have labels. So in labeling the nodes is one of the most common practice to schedule workloads inside a specific node. And we have here a maximum of 10 size that will serve the minimum required workload for application. But then we have a list of worker groups launch template that we configured with spot instances. And the spot instances here, we have two special arguments. One is the lifecycle spot, so that you can either schedule with no selector, and the other one will be a taint that will use a key spot group with the name of the group we want to target for toleration, so that we can decide if certain workloads are suited for spot instances or no. And the prefer no schedule is one of the three options: no schedule, prefer no schedule, no execute, that you can use, and we saw it working pretty well for our needs. And the last argument is something that we really stumbled upon by chance. Basically, when you are working with spot instances, they apparently don't have the same, let's say, resources usability. So they are going to be affected a lot more by noisy neighbor phenomenon. So we had to flag a specific CPU reserve memory and CPU system reserve for kubelet, because we observed that in spot instances where we had many more workloads, so the workloads were more packed than on the on-demand instances, we observed the kubelet sometimes was performing badly, and we couldn't really find any other explanation than increasing the available system reserved resources for kubelet. So this was our implementation. I hope you found some tips and tricks that might be useful for you. One more is that we use the same type of instance here between, the 4x large here is spread into different 4 types of instances. This is very important when you create a spot worker group with a single taint to enable you to decide the price that you want to bid for a spot instance. For example, here we don't specify it because we were accepting any price below the on-demand. But what you could do here is defining a bid price for the spot instance group, which is either very low or someone in the middle or very close to the on-demand. And what this will do will enable you to schedule workloads with priorities, which means that when you want to be sure that your workload will be scheduled on a spot instance that is somewhat available because it's close to the on-demand price, you can create a toleration in your workload for a spot instance group that has a higher bid price. While instead, for jobs that do not need any guarantee that need to be run, you will be able to use the much lower bid price. So even if the bid price, even if the spot instance price is higher than that, the spot instances will not be scheduled, but you will not have to worry because you didn't really care about that workload. A final word, as I said, on cloud readiness. We could not have done any of this if the product team working on the applications that we tested in the cloud for 2 weeks. So we ran in production the workload. So we served our production traffic for those applications for 2 weeks. If the team would not have worked with us by optimizing the way they use resources like caches and databases, by optimizing monitoring and logging and observability and optimizing the startup times, we would never been able to declare our POC successful. Because in the first iteration, our average scale time was between 2 and 3 minutes. So in 2 minutes, when you have a traffic peak that goes like, I don't know, up 20 or 30%, you're done. While instead, with the third iteration, we were able to scale up of tens of instances in 30 to 40 seconds. So given that the node is up and ready in 30 seconds, it means that in a minute, we are ready to double our traffic and to reduce our latency spikes. Combined to the fact that we were using custom metrics to drive the scaling, This allowed us to have very good results. So why you need a cloud readiness checklist for applications? Because it's not only infra. Most of the things that drive infrastructure are in the code, are in your applications. So if your applications are not cloud native, so if they don't have ability to expose their healthiness, ability to be terminated anytime, and graceful shutdown, their connections, if they don't have these attributes, don't even try and pour them to the cloud because they will not work. So if you stick your Tomcat in a container and put it into Kubernetes, this will not solve your scalability problems. So we introduce our checklist for applications that want to be deployed in this new system. They need to have monitoring, logging, and observability baked in. And fortunately, we have these out of the box for our product teams because we have an internal framework based on Spring that gives these features. They also need to have lifecycle hooks that works. So when the application is broken, it does have to fail as fast as possible. And when the SIG term of the container is sent, the graceful shutdown needs to be very graceful. So no connections lost unless there is a huge problem with it. There needs to be health checks in the applications. So liveness and readiness needs to expose if the application is healthy and ready to accept traffic. And also this is baked in our framework. The application can identify by itself problems on other resources that it needs to be working, like DBs or caches, and report eventually those in forms of metrics or traces emitted. We declared that an application that wants to go in our cloud system needs to start up and be ready to accept connection in no more than 30 seconds, because otherwise all of our reasonings on scaling speed were not worth. And also the applications that needs to be deployed in such cloud, they should not rely on any state that cannot be handled via network call, which means no local storage. And also no special configurations like memcached version 3, or no special resources that cannot be offered by a managed service in the cloud. So for example, our applications were using Hazelcast as a cache service, remote cache service. We had the product team migrate to Redis because Redis is offered via Elasticache. We use internally a special implementation of MySQL with esoteric engine called TokuDB that is optimized for writes. We replaced that with DynamoDB inside the application because TokuDB is not available as an engine in RDS and probably will never be. So the application needs to adopt the managed service offered by the cloud. Otherwise, you lose any advantage importing your applications inside a public cloud. Once this is ready, everything can work fine. And finally, the results and what we got out of this nice experience. So we had a 20% improvement on the 95th percentile of response time. Here you see the average response time for the whole funnel of searching a flight. It's 15 seconds might seem very long, but consider that we have to go to fetch multiple providers via network calls and then combine them and then do all the operations on the data. So we were still pretty happy of a 20% improvement, but the most relevant result was that we actually did increase our ratio. We were having a 99.97 availability with 1/3 of all resources. So consider that in data center, we have 100 for resources. We were able to increase our availability by 0.7% just with 1/3 of 100. So with 33 of resources. And this was staggering. When we looked at the data, we knew we did it right. And also, this is a CloudWatch dashboard. If we see the period that we served production traffic from our EKS implementation compared to the data center, we don't have special spikes in CPU usage. So the average of the CPU usage of the nodes is pretty constant day by day compared to what we are used to seeing in the data center. So we were able to use the spot instances that are now in green to absorb the traffic spikes that we had. And basically, this is a pattern that our website follows during the day. So very quiet in the morning, then we will pick up in the night, and then we go down again. And so also we were pretty happy with these results because it means that we have a stable consumption of resources. We don't have problems in our implementation that needs to be fixed. But it's not over yet. So we are not done. We have other challenges when we will effectively run other workloads in production with this system. How are we going to handle stateful set? So how are we going to leverage EKS to run stateful workloads for our systems if we ever need to? We should use vertical pod autoscaler, not only the horizontal pod autoscaler. So vertical pod autoscaler is a fairly recent object in the Kubernetes API, but basically enables you to increase or resource the resources of the single pod dynamically, which is pretty powerful because you might have sized a workload in a way that is not proper. If you are wasting resources, vertical pod autoscaler can remove those resources that are not used. Also, we would like to scale on more metrics. Right now, we were scaling on GC time and network connections per backend, but why not scaling on other infrastructure metrics like DynamoDB connections or anything else that influences the behavior of your application? We would like to introduce kubejanitor. Is also a project from Zalando team. This is a project that will find unused resources in your cluster and will, just clean it up. AWS Node Terminator, I mentioned it earlier, should replace now Spot Termination Handler, which is the project that say signals to Kubernetes to drain nodes that are going to be terminated in spot groups. And then we should introduce a pod disruption budget for our workloads that are scheduled to the on-demand instances, because since the on-demand instances are also scaling up and down, we need to introduce a budget of pod that will serve the minimum amount of traffic for our applications. We did not have the time to do it, but it's certainly something that we are evaluating for our next iteration. And so something about us. We are here. That's my pick. You can find me on the internet with the Inge4Press handle. And of course, a shout out to the whole team that made this possible. So my colleagues, Andrea, Massimo, Paolo, Luca, Alessandro, Stefano, and the product team developers that helped us drive, product increments for the application, Giuseppe, Vittorio, Denis, the tech architects that followed us in implementing our architecture, Massimiliano and Sergio, and the AWS team that were the two guys that helped us implement all of this with suggestions, tips, and tricks on the trenches. Here you have our blog. Check it out. It's cool. And our careers website. Take a look. We are a good tech company, and we are also hiring. So check it out. And with that, I thank you all for listening so long without any question. And if you have any, I'm happy to try and answer some.
Thanks so much, Francesco, for the brilliant presentation. Learned a lot. Hope all other lovely attendees too. There are a lot of questions. I start at the beginning. The first question was, why are you symlinking I think you mentioned the TF bars. Does that work well with Jenkins? So
I mention it here. So it's something that does that work with Jenkins. As long as Jenkins supports a file system that supports symlinks, I'd say yes. Because actually the file is visible inside the project. I don't know if I can share it. I will try. So let me check. So yeah, here. So I don't know if you maybe it's better if I go into presentation mode. So this is our project. Actually, it's kind of a copy of it that I cleaned up for this presentation. Enter presentation. I don't see it. Well, whatever. You can probably see there is a symlink here, and yes, it worked pretty well for us, defining the file outside and then linking into the single projects enabled us to have common variables just in one place. And then we override it with locals.
okay, very nice. Thank you. The next question is from AJ. He's asking, are you using tests for the Terraform like Terra tests?
No, we haven't. So this is something that we evaluated, but none of the team had actually any experience with it. And so we actually used a test suite based on API calls. So we use Golang, and we did implement tests against the built infrastructure by any single stage.
Okay, thanks so much. So the next question is from Ziprun. He asked about TF state, Terraform state. Is that saved in S3 or in GitLab?
No, definitely S3. We have since we are adopting Terraform for many projects, we have a configuration in our cloud by which we can let's say we have multiple buckets with the Terraform states, and we have a convention to reference every state for every project. So yeah, they are of course in a bucket with versioning, with redundancy, and super secure. We did all the things with security, but yeah, that's the remote state is the way to go when you have such configuration, because you cannot risk of overriding states between iterations.
Yeah, sure. Thanks so much. So the next question comes from Vyacheslav. I hope I pronounced the name right. Are there any secret management solutions implemented?
Okay.
Asking something like having HashiCorp Vault or something else.
We are in a process of evaluating it, but we did not need one for this specific implementation because we leveraged the only secret that we needed basically were access keys to other resources. So we leveraged this mechanism. Sorry. So we leveraged this mechanism of authenticating and authorizing applications via provider federation in Kubernetes. So once we defined the proper IAM roles and annotated the workloads for applications, we were able to connect to the other services. So no, we did not use Vault. We don't yet use Vault in our infrastructure. We have, let's say, a in-house secrets management solution that was developed by the team long days ago, and that we are trying to dismiss for using Vault. But it was not necessary in this project. The only credential that we used and we stick it basically in a GitLab CI store, a variable store, is the password for the service account that we created inside Active Directory to connect to IAM and being able to execute Terraform code, so to instantiate the Terraform provider. So that is also done via ADFS. So we have a unique password for a service account, we put it into GitLab, then GitLab calls Python utilities that is called ADFS login or ADFS AWS, I don't remember.
Yeah.
And that is generating the credentials via STS token. Then these credentials are saved for later use in the pipeline.
Awesome, thank you. The next question, also from Vyacheslav. How long did you need to implement this architecture?
If I get the question is, how much time did it take for the team for?
Yes. How much time did you need? Needed to implement the whole thing?
So the whole project was around 2 months. And consider that in the last 3 weeks of the 2 months, we only ran workload in production. So we served the production traffic for our applications inside the KS. So I would say that it took 5 to 6 weeks to complete the all 3 iterations. And I say, if I remember correctly, so we started in November with this implementation. We already had some ideas because this is part of a bigger project. Since we had to connect the data center with the KS to serve production traffic, we had, let's say, an initial phase where we set up all the things in our cluster, like external names, VPNs, stuff like that. But the focus on these activities was, I would say, 2 weeks for the first implementation, then another week or 2 for the V2, and then another week for introducing spot instances. But consider that we were 5 SREs working in this project, and other 3-4 product engineers and 2 architects. So yeah, I would say 5 weeks. But consider that if you check out our blogs, this will be probably open sourced in a blog post from ours. So you will be able to get this for free in 0 days.
Wow, brilliant. Thank you so much. Yeah, and that was the next question. Are you going to open source your implementation on GitHub?
I mean, we need to clear some of the concerns, some of the things that connects, let's say, the projects to our data center. But I think it's feasible, at least for the infrastructure part. So the one that we just saw in the slide, the one that you see, for example, we have seeds that are not variables here. But definitely, I think it will probably be online by the end of the quarter. I don't know. So the one that will be writing the blog post will be me. So it depends if I find the time to do it. But yeah, we willing. I mean, we would really love to open source this work.
Yeah, if the security allows.
Yeah, that's
one of the main problems. We love to open source as well, what we are doing always, but in some cases, it's not so easy. Okay, the next question is from Roman. Are you using multiple AWS accounts?
Yes. So the design is maybe I had a slide on it, but I prefer not to show it because it's probably difficult to read, but you are now seeing it. So so basically, yes, each one of these is an account, And it's impossible to read, but basically there will be an account with the global resources shared by all the accounts, so the other accounts, and the global account will be responsible, for example, for IAM federation, main connectivity between data center and AWS, NAT gateways. So DNS is very important. They better have a central DNS store with if you are hybrid cloud, you need to have data center DNS and EK and AWS DNS. You will need to centralize it. And each of the, let's say, group of applications that are going to be targeted per funnel will have one or multiple accounts. I think in the final design, yeah, in the POC that we did, we used 2 accounts. But in the final design, we aim to have at least 6. Because each account will be containing, for example, test resources, or we can spin up cluster on demand in an account dedicated for stress testing. So there will be a functional splitting of accounts in the final design. We are discussing it, these days, but yeah, using multiple accounts has a lot of benefits because you can federate identities, which means that you can use IAM roles given by an account to authenticate 2 roles provided by another account. And this is ideal if you want to do authorization federation with IAM. So you will have the global account in which you federate your authentication and authorization, and then the permissions will be carried over to the other accounts that you are allowed to access. So this is the way to go.
Thank you. Very nice. The next question is coming from Prakash. He's asking, what is the IRSA architecture that manages invoking external APIs, accessing external FTPs or other on-premise systems?
No, I don't think so. I mean, this is, so IAM role for service accounts. So IRSA means IAM roles for service accounts, which means that the pods will be mounting a service pods inside Kubernetes nodes in EKS will be mounting service accounts with the ability to generate STS tokens, provided that the STS tokens are connected to an IAM role. So this IAM role will only be able to connect, to authorize access to other AWS services. If you have an external service like FTP or SFTP or another API that needs JWT token, you will have to use a secrets management solution, say Vault, to inject these credentials inside the pod as well.
Sure. Yeah. Thank you. Thanks so much. Another question from Vyacheslav. With regards to security, do you use publicly available Terraform modules hosted and maintained by third parties?
Yes, we stick with the official, so the Terraform modules. But in some cases, we've also adopted community modules. And this has never posed actually a security issue so far. What we find useful in the community model is that we can take a look at the code and take a look at the source. We don't have yet any security scanning for Terraform modules, but I think it's feasible since the code is open, and we never felt the need to. So.
Okay. Yeah, sure. That's the same case as by us. The next question is why you decided to using Nginx controller, ingress controller, instead of ALB, application load balancing ingress controller.
Okay, this is a good question. And the response is, well, first, we already use Ingress Nginx in our cluster, where is a bare metal cluster. In our clusters, actually, in our production clusters already use Ingress Nginx. We use it since the age of times, so we also contributed to it. We are very familiar with it. And so since we are very happy with it, and since we had a requirement, which is to be able to serve a canary, so a portion of the traffic from the AWS infrastructure while we are still using the data center for serving majority of our traffic, we found an implementation that was working for us very well with Ingress Nginx, that is Ingress Nginx Canary. So what we did, we configured a network load balancer, so layer 4 in AWS. This network load balancer was then dispatching the request without any HTTP filtering to Ingress Nginx. And since we have host name splitting depending on the application that needs to be served, we felt comfortable with Ingress Nginx. In the data center side, we have 2 ingresses for every application, and one is flagged as a canary. And with that mechanism, we were able to immediately, so in a less than 50 millisecond, route a variable percentage of traffic for the services between data center and AWS. So I remember one day we were testing the autoscaling, and the way we tested the autoscaling was we started with 100% of traffic directed to the data center, and then editing the ingress with a different weight on the canary, starting with 1 to 5, 10%, we were able to see if growing the traffic directed towards the AWS infrastructure was effectively scaling as we expected. So the reason why we use Ingress Nginx, I think mainly because we are very comfortable managing it. While application load balancer and elastic load balancer, yes, we have used them in the past, but we really didn't know other parts of it, like TLS, certificates, etc., etc. So it was fairly straightforward for us to replicate our infrastructure in EKS because we have everything packaged as Kubernetes manifest.
Yeah, sure. Thank you. The next questions come from Prakash again. How do you manage OS patching, updating AMIs, how you train node groups and switch using Terraform?
I think we never did. So I guess we used this. I don't know. I mean, we leveraged the module that might have adopting the default MEI for the EKS worker groups. And we actually wanted to avoid managing such things because we wanted to hand off the burden of security upgrades, etc., to the cloud provider. So that's why I don't have an answer for you. I mean, definitely in the past, and for other clouds, we use Packer, we build our MEIs, and in our data center, we have Foreman and other mechanism to provision virtual machine and keep them updated. But here, one of the main goals was not have to manage it. So actually, I have no idea which MEI we used for the worker groups. And I think it's good that I don't know, because it's one less thing to cobble in my mind.
Yeah, perhaps from my experience, we was using also the Ubuntu with EKS, or we switched to Amazon Linux for certain reasons, for security. And if we want to patch with autoscaling and spot instances or running instances, we delete them and they will get recreated, and they will get the latest patch. So delete and you have the latest patch.
Not bad.
The next question comes from Tambura. What did you use to create the nice looking 3D infrastructure slides?
So this one, it's an app called Arsery. I used to use Cloudcraft, but I could not use it. It had some limitations, so I used this Arsentry here, arsentry.com. I can share in the chat.
Very nice. Thank you very much. Yeah, we are using Cloudcraft as well, but that looks very nice. Thank you.
It probably works better with more resources, because it looks like a little bit of a pixelated effect, but try it out.
Okay, the next question. Are you using Java app? Also, what steps you took to reduce the startup time? How are you managing CPU spikes and autoscaling during pod startups?
Okay, I can give some of those information, but I will not be your Java expert. So if I remember, for what I remember correctly, basically the product team and our engineers went into analyzing what took so long to start up. Consider that one of the applications that were part of this POC was loading at startup time all the dependencies, and these dependencies are basically clients, beans in the Spring way, that are HTTP clients that are used to connect to third parties to fetch the data about travels that the people want to buy. So imagine this application that as soon as it starts, immediately allocates hundreds of resources in a connection pool ready for being consumed when the application is declared ready. So if I got the question correct, is how did you manage to reduce this? Basically, there was a huge work also with the business. Oops, sorry. So the application is, the application was not say re-architected, but was analyzed since a long time that it was not used. And the team said, but do we really need to instantiate all of these beans and all of these connections to the provided before we start? How long does it take once we are starting up to load these resources? So they were able, using a lock system in Redis, so on Elasticache, to synchronize the ability to create such clients. And working on this, basically they removed 50% of the startup time. So I technically don't know much more on the details, but what I can say is that, of course, most of the time was not part of infrastructure. So most of the time required for scaling is effectively code, and especially with Java. especially if you are using Spring, especially if you are on top of Spring adding more dependency runtime injection and more initialization. What is safe to do is leverage the readiness endpoint of Kubernetes lifecycle hooks. So how we avoided to serve request by an application that is starting up, so that is using a lot of CPU and doing a lot of allocations and probably also garbage collecting while it's starting up. How we avoid that it also gets more load by getting requests is using the readiness endpoint. So this feature is, since Kubernetes 1.0 probably, you can configure an endpoint in your application that Kubernetes will call continuously every 10 seconds by default, if I don't remember well. And this endpoint will have to reply to Kubernetes with a 200 OK or no, if it's not ready to accept traffic. So if you configure properly in your system, and I'm sure Spring Cloud has it, this readiness endpoint with all the due checks to declare the application healthy, you are not going to worry about the CPU spikes, because you will not have them. Basically, you will just say, okay, I'm now done with initializing my app. I can now accept traffic. And since then, you will start loading the items into memory with the request that comes in. Most of our framework is using a concept of async initialization, which means that we'll check the connections to database, pre-warm the caches, create beans that are necessary for making the application work. And then when all of this initialization work and CPU intensive work is done, the readiness endpoint will reply, okay, I'm ready, and the traffic will start to be routed inside the pod by Kubernetes.
Right, thanks so much. The next question comes from Bernhard Müller. How did you find out the best relation between Spot instances and the on-demand instances? What was the relation you decided on?
I don't remember if it was 1/5 or 1/6. Let me. But anyway, it was between around 15 and 20% of the whole workload, because it depends on the traffic you have. So say that in the night, your traffic is for a service is 100 requests second. Say that during your peak, your traffic is 700, or let's say 1,000 to make it easy. In the peak traffic, you have 1,000 requests second for a service, and in the very low of the night, 100. So you can tune the ratio to 1/10, because you will never have less traffic than 1/10. So that's how we based our measurement. For our case, we are having a pattern of roughly, say, 200 to 700, 800 in the night, so where we have the peak, but we don't have huge spikes. It's a, let's say, 2% minute increase that can be handled pretty well with autoscaling.
Okay, thanks so much. Dimitra asked about why not to use dynamic overscaling in K8s.
Say that again, I didn't understand.
I don't understand the question really myself. So why not using dynamic overscaling or autoscaling in K8s? I think, okay.
How do you measure requirement? Any APM? Okay, I'm scrolling through the question to see if I find it. Why not to use dynamic overscaling in Kubernetes, which is cluster autoscaler? I don't know what is dynamic overscaling. It's the first time I hear about it.
I think he's thinking about over provisioning. That is, that you simply over provision a given percentage of nodes, and then you just don't have the problem of startup times.
Yeah, that's what we did with the on-demand. So we already have on-demand nodes ready for the minimum traffic we have. And we cannot go any lower than this. So we are fine to pay on the on-demand. And then when we need to increase our capacity, we scale with the spot.
Yeah, so in our case, we are not using any on-demand. We are using 100% spot instances, and it's enough. Okay, Prakash asked about, did you face any app disruption in parts, production environment using Spot?
The 0.03% that we measured that. So this is mainly due probably to the spot instance being terminated before the drain is really completed. But if you use a mechanism of gracefully shut down your applications, you will not have this problem.
Okay, thank you. So I have to jump over some questions. Comes from Yesh about we would like to see some Terraform code. I think you.
Yeah, I confirm we use the public Terraform module for EKS to provision infrastructure, and probably I will be able to share the code on GitHub in our organization as soon as I isolated the minimum required to make it open source, so that I don't leak, I don't know, IP address, etc.
Thank you. The next question from Vyacheslav is about, are there any APM solution being used?
So no, we rely on our Graphite and Prometheus stack. Basically, it's not shown here for space reasons, but this Prometheus was, where is the pointer? I don't know. This Prometheus here was created alongside the Kubernetes infrastructure in AWS, but we also have a data center Prometheus and Graphite and Grafana stack that we use for monitoring and observability. So the metrics were scraped and sent to both by this Prometheus here for what we needed for autoscaling, but were also sent via federation to our internal Prometheus, and were also pushed to Graphite for metrics evaluation and reporting of business activities.
Excellent, thank you. So Alexander Giza is asking about, how do you measure the resource requirements for the application to determine the sizing of the instances?
This is an interesting question. We spend quite a lot on this, probably one whole week, trying to find the better size of our instances. And basically, the key to our reasoning was this one. Say that your workload will be restricted to maximum 6 core and 4 giga, or 4 core and 4 giga. So you know that you want to dedicate a spot worker group for a workload that is stateless, and that in maximum, let's say, limit of the pods will be 4 core and 4 giga. And you basically have to adopt a formula by which you will subtract from an instance the number of pods you want to serve out of it. And then there will be enough space for kubelet to perform properly. So we, for example, identified that we could run on a specific application. We could have an autoscaling of M4 extra large, so 4 extra large instances, cluster type. And in that, since they are, if I remember correctly, 16 core and 32 giga, we could fit no more than 6 pods. So since our unit of scale is also 6 pods, that was the correct size of the instance. I try to put it in another way. We created a formula by which we said, whenever we need to scale, we need to increase our capacity of at least X%. Since we want to do this on 10 instances, when we add the 11th, we need at least to schedule 5 pods on it. So to schedule 5 pods of limited to core to 4 giga and 4 core, we need a M4 extra large instance. So we got that type of instance for that workload. I hope this is
very nice. Okay, the next question comes from Yesh again about the upstream module, and they are facing some issues which they are not getting resolved with the work
control of our work. So we only encountered one issue with this module, and we solved it by using protect from scaling true. So basically, even if you don't specify scaling policy for these worker nodes, apparently AWS will shut down the nodes that it does not declare needed. And setting this worked pretty well for us, in the sense that we were able to drive scaling via Kubernetes. So it was the cluster autoscaler that was driving the scale in and scale out of the nodes, and not AWS. Because if you get mixed policies, like cluster autoscaler want to scale down, a autoscaling group want to scale up, this does not work well. So I hope this can be helpful for your project. Protect from scaling true. And the scale out was never an issue for us, as long as the proper metrics were in place. Basically, one detail that I didn't mention is that the cluster autoscaler will only scale once it detects that are unscheduled pods that needs to be scheduled. So it's a continuous loop between HPA that requires new pods that needs to be scheduled by the control plane, cluster autoscaler that verifies if these pods are scheduled or not, and if they aren't, we'll create a new node where it needs to be.
Very nice, thanks. The next hint from Oleg is about to avoid symlinking, you can use TerraGrant. Are you using TerraGrant?
Actually, no, there was one colleague that had used it in the past, and since he was the only one out of 5, we didn't set it up. But we are looking to adopt it for the future. It's a nice tool. I used it only once, long time ago, but since this colleague is knowledgeable, probably in the next project we will adopt it.
Very nice. So Thanks. The next question is about Kube to AIM or IRSA. I think that was answered. You are using IRSA.
Yes.
Services. And from Dimitro, addition to previous, maybe KIAM. Okay. No.
KIAM. Yeah, no, never needed actually. But if it helps authorizing to external services, maybe we can evaluate.
Yeah. Are you planning to inject some mesh like Istio or AppMesh?
So since we don't have any mesh in our current cluster, we are also evaluating to adopt one by the end of the year. The main advantages that we would have are some of them are already inside our framework for applications. So like, HTTP throttling and telemetry. So if we find other benefits, we might evaluate to use it. And also, of course, UpMesh would be our choice.
Yeah.
With regards that we need to have it working also in the data center. So we would not like to have a split cluster setup where we have data center with no mesh and cloud with mesh. So probably also Istio or another product is going to be used. But so far, we have an idea to try and that, but we don't have a strict need for now. Let's say like this.
Okay, thank you so much. So I think there is a hint from Sigrun about usually the Terraform Cloud Formation template get the latest AMI for SSM parameter that AWS is maintaining.
Awesome, thanks. That's what I hoped.
Yeah. Okay. Comparing to use the next question from Dimitro, comparing to use on demand and graduated resources and all spot with over provisioning, I guess better to use last one, especially when it comes to costs.
Could be, yes.
Yeah.
Yeah. We will continue iterating on this. Our final implementation was not iterated any longer because we were running out of time and we wanted to serve production traffic out of our new infrastructure, new shiny infrastructure. And we really wanted to see the results of running 2 full weeks of production workload in the cloud. But yes, we will start from there. Our work is not over, and we will always have to reduce costs because management always will ask for more savings. So
Yeah, sure.
We will see.
Yeah. Thanks. Chris Stefano is asking, with metrics playing such an important role in the scaling logic, what HA considerations were taken to make sure SLAs were met?
So if I understand correctly, it means how did we ensure high availability for the cluster with regards to the fact that we act on scaling based on metrics. Am I correct, Chris? So I don't know if yes. Okay. Yes. So basically, we ran out of all 3 possible availability zones, and we knew we would incur into a higher cost than running into only 2 availability zones. And what we leveraged was the fact that when you deploy worker groups spread to subnets that are deployed in multiple availability zones, you spread in multiple availability zones, you can leverage native AWS redundancy of the availability zones. So as far as we have enough subnets to schedule our workers on, we will not have an high availability problem. And we did not actually went and look into how to design our workloads to be spread into multiple zones, like using anti-affinity or stuff like that, but because we basically handed off to the scheduler of the EC2 instances in the worker group. So we really did not worry that much that we were serving the workloads out of the 3 zones. Actually, we probably we didn't even measure with a metric if we were serving an equal percentage of traffic from the old zone, from all the availability zones that we adopted. And we said, let the cloud handle it. We create enough subnets for scheduling our workloads and enough nodes that they are spread on these subnets, and the rest will go by itself. And actually, so Kubernetes did a pretty good job scheduling these pods in a highly available manner. Not sure if I replied to your question.
I guess I was more concerned about the cluster running your metrics, so the Prometheus part of it.
Ah, okay.
So, you know, if Prometheus goes down now, your autoscaler is not going to go up. So you can increase of traffic. Eventually, your pods are going to run out.
I see what you mean. So how we adopted an highly available Prometheus?
Yeah.
Well, it's out of scope. Yes, we we leverage the chart, we leverage the storage, etc., etc. So we didn't adopt Cortex or Thanos or stuff like that because we already have a lot of that in our data center. So we really didn't want to have a huge setup. But yeah, I definitely have a good point, because the Prometheus becomes a core component. So it needs to be up and running for scaling actions to be evaluated.
Thank you.
Thanks so much.
Cheers.
So there are a lot of questions.
I see.
Okay, so that's a meetup and open end. I hope it gets at least your questions answered at the end of the session. If not, we will schedule another session with you, and we have to postpone Alex's session about RDAS to our next meetup. But the next question comes from Hugo Francesco. While using EKS, we usually hit a problem with it not being very optimized for cost. For example, because Kubernetes scheduler puts pods equally in every node sometimes over the time, and we end up with lots of the free RAM in every node, which could Okay, yeah.
I read the question. So the short answer is no. You cannot configure deployment of the controllers of Kubernetes as you would do in a regular Kubernetes install. So in EKS, you cannot, for example, set the threshold for autoscaling. You cannot configure the scheduling mechanism, etc., etc. What we found very useful was using the taints and tolerations to pack as much as possible with the limits mechanism, as much as possible pods inside a node. And when you find yourself having one only node that is below the 50% of usage, cluster autoscaler by default, which is configurable on this one, will delete the node. And Kubernetes will try to reallocate the pods into other nodes. So what I would advise is to check the cluster autoscaler configuration, which is somewhat very good. I mean, it can be tuned. And also decide very well the sizes of your nodes, so your instances, the instance type that you choose with regards to the limits that you want to adopt, so the C group limits for your workloads. I know the C group limits is a huge pain point because in some kernels can cause performance degradation, but for us is a key feature of this project that enabled make scalability and scaling reasoning around, the number of pods that can fit into an instance, the number of nodes that we need to serve the whole 100% of traffic. So how to size the autoscaling group of a certain workload. All of this was possible because we started from defining the limits of an application, so of a single instance of a pod. If you do that consistently, and you spread, and you adopt multiple tiered worker groups with taints and toleration, with labels to schedule pods where you want, in the end, your design should be maybe not effective as running on VMs where you have more control, but for sure similar to that.
Okay, thank you. So the next question comes from Dimitro. Did you check the KEDA as a tool for matrix autoscaling? GitHub KEDA.
I've heard of KEDA recently, so it's something that I think works like an event bus for Kubernetes. But no, we didn't use it yet. I just took a look into the GitHub project. Looks very interesting, so thanks. Maybe it's going to be part of our next iteration as well.
Yeah. So what I guess so, KEDA is most coming from Microsoft for Azure.
But I think it works for plain Kubernetes. If I remember, yeah, that was it. Kubernetes event-driven autoscaling. I stumbled on the website pretty recently, something like 2 weeks ago, and we can speak with our team if it's worth evaluating it. It looks promising. We will see how it goes.
Yeah, interesting. Thanks so much. The next question comes from Bala. In recent Fargate was not used instead of EKS?
Yes, it was not released at the time of the POC. So it was released in December, if I remember correctly. So even before in reInvent. So there was Fargate for EKS announcement, but since we already designed most of the infrastructure, we didn't use it.
Yeah, so from my experience in our project, we evaluated Fargate as well, and there were some blockers. So regarding CPU and RAM limit or ports, we was not able to use Fargate. Yeah. For one of the projects, so where we are going to use Kong as API gateway. By the way, are you using any API gateways?
No. I mean, you could say that Ingress Nginx is our API gateway because it's really there where we split our traffic. So we found it very useful for our data center. We have a lot of control on the requests path, and maybe not so much telemetry, not so much features, but it worked pretty well for us. So we could say that we are using it as a semi-API gateway.
Okay, thanks. Yeah, we are in the process to have Kong in place as the API solution, a gateway solution.
It's a nice product. I have seen a couple of demo
for service mesh, and you're evaluating the whole thing. But yeah, Kong is, I think, decided to use Kong. Great solution. Perhaps we can provide a session about Kong by one of our next meetups. Okay, the next questions comes from Bala. any security best practices, tips, and tools when on-prem and cloud are connected?
Security best practices. Well, we operated VPN, and actually I did not follow that part a lot, but basically we were able, with our data center connection towards Amazon via the VPN, we were just able to, instruct our data center networking how to route traffic in and out between AWS. So I guess my only advice is not security related, is to manage AWS as much as possible what you can manage in AWS, because being API driven compared to some data center tools where you might not have a lot of automation, you can do much more in AWS with the software-defined networking implementation they have, compared to the software-defined networking that you would purchase from a vendor. So security best practice, we basically had all of our databases in the data center, and the applications were connecting back to the databases, but we moved the caches, of course, for latency and bandwidth reason, and in AWS. So what we had to do basically was create security groups and network ACLs that would allow the pods inside EKS to connect back to the databases, and that would never instead allow other applications that didn't need to connect to the caches pass into the VPN. But that was done mainly in the data center side. So I'm not a very expert in security, networking security especially, but yeah, the only advice I can have for you is manage as much as you can in AWS.
Yeah, very nice. Thanks so much. The last, I'm not sure. There are a lot of compliments to you, and thanks for your presentation.
It was great to be here.
Really 2 hours. It was really nice to have you by us. The next session or presentation from Alex will be postponed.
Sorry, I
Hopefully
didn't mean to.
in 4 weeks, I hope. We'd love to invite you again to learn from you, Francesco. For myself, it was really brilliant. Thanks so much for the great presentation, sharing your experience, your knowledge with the community, and how we can have you by our next meetups, and perhaps after Corona, meet you in person by KubeCon, hopefully in Amsterdam, which was canceled. And yeah, I think if there is no other questions, like to thank you again. Let's keep in touch.
Actually, thank you for hosting the meetup, and to everybody who participated. It was. I hope that I can, I can send you something.
Yeah. Thanks everybody for joining and for your patience. 2 hours at this late time in the evening, at least in Europe. Thanks again, Francesco. Hope to meet you in person soon after this crisis, which we have with Corona. Some day, perhaps in Italy, at your side, and take care.
Thanks. And you too, stay safe, stay at home, everybody, until this madness ends, and we will get out of it. And
Yeah.
let's keep coding.
Yeah. Thank you.
See you next time.
Thank you very much.
Bye-bye.
Ciao, everybody.
Bye.